Hi and welcome to my series on solving the wave heat and Laplace equations. In this video we'll be solving the Laplace equation with Dirichlet boundary conditions. As a prerequisite, you should be familiar with solving first and second order linear ordinary differential equations, and preferably you would have been introduced to PDEs as well. But really quickly, here's a summary sheet of a few things you should pay attention to. We're doing the Laplace equation over here. You'll see we have 4 boundary conditions, so we have no initial conditions here. We're going to get 2 ordinary differential equations. One of them will have a plus and one will have a negative sign. The plus is going to go with the variable that has the 2 homogeneous conditions. We're going to be working with Dirichlet boundary conditions, so our eigenvalue is going to take the form of n pi over L, and we're going to get an eigenfunction of which takes the form of a sine function, and our associated eigenfunction t of n is going to contain the hyperbolic cosine and hyperbolic sine. So the first thing that you're going to want to do when solving any equation really is to interpret what the question is asking of you and what it means. So in the Laplace equation, which is also called the steady state heat equation, we don't have any dimensions of time. What we have instead are 2 spatial dimensions, x and y. So if we call this x and we call this y, we can see that our x ranges from 0 to 1. So we'll say x is 0 here and this is 1, and we can see that our y goes from 0 to 2. So this is not to scale here at all. I've drawn this really badly. But down here, u equals 0, u equals 0 here, u equals 0. I'm talking about on the boundaries here. And we have u equals sine pi x on this boundary up here. So all that steady state means is that the temperature at different parts of the solid remain constant, so it's independent of time. So I'm just going to write this down. Steady state means that the temp at different parts of the solid remain constant. So we're talking about something that is independent of time. Now, if I've made any spelling mistakes, well, just know I'm a really bad speller. So, all right, so step 2. We need to identify if either x or y is our variable with our homogeneous conditions. So identify if x or y has the homogeneous conditions. So in our case, we can see that it is our x variable that has, because these are our homogeneous conditions, whereas this, our y variable here has one non-homogeneous condition. So we're going to, this is just going to affect how we write our ordinary differential equations. So I will show you what I mean by that when we get to it. So that was step 1. So step 2. So in this case, in our example, it's x that has our homogeneous conditions. So therefore, I'm going to write our 2 ordinary differential equations as this. Now I'm going to go through and do the whole process, but I'm just going to show you what I'm talking about now. Minus lambda squared y equals 0. So I'm always going to write the one with the 2 homogeneous conditions with a plus. So if it was y, I would put the plus in with the y, and I'd put the minus in with the x. And this is really just so we're always doing the same sort of boundary conditions and the same equations for at least half of our workings out, which really just helps us not to get anything wrong. Well, decreases our chances of getting things wrong. So what we're going to do is to go through the process of separation of variables. So we're going to assume the solution. So we're going to come back to this. Assume solution of PDE takes the form of u of little x of little y equals big X of little x, big Y of little y. So if we sub this in, so subbing into the PDE, we get something that looks like this. X, Y double prime plus X double prime Y equals 0. So if we go to step 3, use separation of variables. If you've watched my other video, you already know this, but separation of variables is just where we put all the x's on one side and all the y's on the other side. So when it comes to separation of variables, I'm going to put the minus sign, the variable with the non-homogeneous condition. So I'm going to put it with the y here. Y equals x double prime over x. And if x had the non-homogeneous condition, I'd put this negative sign here with the x instead. So we can say because x and y are completely independent of each other, but yet they equal each other, we know that they have to equal a constant. So we're going to call this constant k. But we know, or at least it is known, that k greater than 0 gives only the trivial solution. We're not interested in the trivial solution because they don't tell us anything interesting. So what we're going to say is that k is equal to a negative lambda squared. So, and this is because k greater than 0 gives only trivial solution for Dirichlet conditions and Neumann conditions. So we're just putting a little bit of restriction on what the sign of k is. So if we then rearrange this, we get two ODEs. So rearrange to get two ordinary differential equations. And these will be lambda squared y equals 0 and x double prime plus lambda squared x equals 0. So you'll see at least the one with this x variable here, you would have seen that plenty of times before when doing either the heat equation or the wave equation, and that is the reason why we choose to keep the x's positive in the line above and put the negative sign with the y, and it's just so we're always working with this same equation here. So this equation really doesn't change from the Laplace, the heat, or the wave equation. So the plus should go with the homogeneous variables here. So x has the homogeneous variables, it also has the plus here. So just keep note, we're going to treat this as just like our normal boundary conditions in the wave and heat equation, and we're going to treat this like our initial condition, even though there is no initial condition here, they're just boundary conditions, but we're going to treat it like the initial conditions in the wave and heat equation. So the next step, so we have step 4. We're going to use this x double prime plus lambda squared x equals 0 with the homogeneous boundary conditions. So if y actually had the homogeneous boundary conditions, we would be talking about the y equation first, and then we would do the x equation second. But in this case, we're doing the x equation first. So now we need to consider, we know that lambda can't be less than 0 because of this restriction up here where k equals negative lambda squared, but lambda could still be greater than 0 or it could equal 0. So we need to consider two cases. One where lambda equals 0 and one where lambda is greater than 0. If you've watched my previous videos or you've done these sort of things a few times before, you'll know that because we're working with Dirichlet boundary conditions up here, you'll know that the lambda equals 0 case is going to be trivial. But for those who haven't seen it, I'm just going to work through that again. So what I'm going to do is I'm going to say if lambda equals 0, we're going to get the ordinary differential equation that looks like this. And the general form of the solution, is big X of little x equals ax plus b, where a and b are some constants. If we put in those boundary conditions for x of 0, we're going to just get b because that first term's going to vanish. And according to our boundary conditions up here, it has to equal 0. So we know that b equals 0. So if we put in our next condition, x of 1, for b equals 0, we're just going to get a times 1. And this also has to equal 0 according to our conditions up the top. And because a and b, so as a and b both equal 0, then we just have the trivial solution. And the trivial solution tells us what's happening when nothing's happening. So while it's a solution, it's not an interesting one. So we're just going to disregard the case of lambda equaling 0. So I'm going to say lambda cannot equal 0. Right, so going over to the left-hand side, when lambda is greater than 0, we get the ordinary differential equation that looks like this. The general form of solution looks like this. Write it down here. Big X of little x equals a cosine lambda x plus b sine lambda x. Where a and b are just some constants. They're not the same constants as over here. They're just different constants. I'm just reusing a and b just out of habit. I do that all the time. So just keep that in note for if you're watching any of my other videos. So now I'm going to put in the boundary conditions here. So x of 0. If we put in x equals 0, the sine term vanishes and we end up with a times 1. So a, in this case, a is going to equal 0. So if we put in our other condition of x equals 1, now a is still 0, we end up with b sine lambda, because x goes to 1, equals 0. Now we could let b equal 0 here, but then we have both a and b equaling 0. We get the trivial solution. Again, we're not interested in that. So we need something other than b to equal 0. So we need sine of lambda to equal 0. And we know when sine equals 0, so we can say that lambda equals n pi for n equals 1, 2, so on. And so n equals 1, 2, so on, because lambda can't be negative, as we have negative lambda squared equals k, and lambda cannot be 0 as well. So when we think of n, also think of lambda, because they're sort of set equal to each other. So this is what is called the eigenvalue here. Our lambda is our eigenvalue. And this is just the value that lambda takes when we get something other than the trivial solution. So we get an interesting solution. So this allows us to write our eigenfunction. So our eigenfunction we'll call x of n, of little x. And we're calling it x of n because we don't know what n is at the moment. N is just some integer. I'll write that here. N is some integer for 1, 2, so on. So x of n here equals sine n pi x for n equals 1, 2, so on. So all I've done here is I've taken this solution, this general form of the solution here, and I filled in what a and b equal. So also note that any multiple of this, so this is called an eigenfunction, and any multiple of an eigenfunction is also an eigenfunction. So also know that there could be a constant in here, and that would also be completely fine. So we could write like a sine n pi x. I'm going to put a box around this. So step 5, we want to consider the second ordinary differential equation. In this case, that's the y1, so the second ODE, but it could very well be the x1 if your y was the homogeneous, had the homogeneous conditions. So this is what the ODA looks like. So in this case, we're just going to look at here the case for lambda greater than 0, and we have the ODE again still takes the same form. So the general form of solution is big Y of little y equals a, some constant a, the hyperbolic cosine function lambda y, plus b hyperbolic sine function lambda y. So if we put in the one homogeneous condition that we have, which is when y equals 0, we just get that a, because the hyperbolic sine will vanish, hyperbolic cosine will go to 1, so we just end up with a equals 0. So this is as far as we can take this one, because the condition is non-homogeneous. So from here we can write our y of n, so I'll write it over here. Y of n of y equals the hyperbolic sine lambda y, and lambda was n pi, so n pi y for n equals 1, 2, so on. So this is also our associated eigenfunction. And we want a box around this because it's important. Right, so step 6, almost there. Step 6, we need to remember at the start when we suppose that the solution took the form of u equals big X of little x times big Y of little y. So what we're going to do is we're going to write our u of n of x and y, and we're going to multiply this by our x of n and our y of n. So I'll just rewrite this again, x of y, because our x of n up the top is a sine n pi x, and the y of n is the hyperbolic sine n pi y, and that is for n equals 1, 2, so on. Now, because any eigensolution, a multiple of an eigensolution is also an eigensolution, so we need to put a constant in here. I'm going to call the constant a of n, but you can call it anything. C of n, z of n, doesn't matter. So I'm going to put a box around here as well, and this is called our eigensolution. Now, we're not finished yet. This eigensolution fulfills 3 out of the 4 conditions that we had, boundary conditions. It doesn't yet fulfill our last non-homogeneous one. So that'll be step 7. Step 7 is to plug in the non-homogeneous condition into our u of n, and then we're going to solve for n and the constant a of n. Right. So let's just recall what the non-homogeneous condition was. It's this one up here. Right, so I'll rewrite that. We have u of x2 equals sine pi x. Okay. So all we need to do is grab our u of n, but in this case, instead of x and y, we're going to put in y equals 2 from here. And if y equals 2 for our u of n, we're going to get a of n sine n pi x over sine 2 pi n. Right, and then we're going to set this equal to what this is equal to, sine pi x. Now what we need to do here is solve for the n as well as our constant a of n. Now it's pretty easy to see here that if n equals 1, then those sine terms, that's meant to be the hyperbolic sign, these first sine terms, this one and this one, will look the same. So let's let n equal 1. Now to solve for our a of n, what we're going to do is just set the left-hand side equal to the right-hand side. And if n equals 1, we can divide by the signs, and we're going to get a of n times the hyperbolic sine of 2 pi, because n equals 1, equals 1. And then solving for a of n, this just means that our a of n equals 1 over the hyperbolic sine of 2 pi. So now that we've got our constant a of n and our n, we can go to step 8. Step 8. And that is to write the specific solution, because we have everything we need now. So the specific solution. So all that this specific solution is is u of n, but we just fill in what our constant is and what our n is. So we can say u of x of y, and it's not u of n anymore. We're using the u of n equation, but it's not u of n because now we know what n is, and n equals 1. So we have u of xy equals a of n, and a of n is 1 over hyperbolic sine 2 pi times sine pi x, because n equals 1, times the sine hyperbolic sine of pi y. Now, in order to get an understanding of what this looks like, I did this earlier on Wolfram alpha. So if I just bring this up here, we get this. So this is what our function here looks like. This is our steady state equation. So it does not vary over time. So the temperature remains constant and is independent of time. And this here is for our x goes from 0 to 1, and our y goes from 0 to 2. And so it just looks like this. So really quickly, just to recap what we did, the first thing we did was to interpret the problem. We know that the Laplace equation doesn't have any variables of time. It is a steady state heat equation. We have our x and our y variables, and they are spatial variables. Step 2 was to figure out whether it was x or y that had the two homogeneous conditions. In our case, it was x. And so when we come to writing our two ordinary differential equations, we put the plus sign here with the homogeneous, the one with the two homogeneous conditions. And that is simply just because then we're always doing the same, working with the exact same equation as our heat and our wave equations. Then we assumed that we could write the solution in the form of u equals x times y. Then we use separation of variables. We put all the y on one side and all the x on one side. The negative sign goes with the variable that has the inhomogeneous condition. And we were able to set this equal to a constant, which we called negative lambda squared. Then we used the equation with the two homogeneous conditions. We used that, and we consider the case for lambda equals 0 and lambda greater than 0. Because we're working with Dirichlet boundary conditions, our lambda equals 0 had the trivial solution. So we ended up with an sine eigenfunction. Step 5 was to then consider the second spatial variable, the y ordinary differential equation. We only looked at the case where lambda was greater than 0 in this case, because it had to be greater than 0 in that second case as well. Step 6 was to rewrite x of n times y of n, which was the very first thing we assumed, was that the solution could be written by x times y. This u of n then takes into account 3 of the initial conditions, the boundary conditions, but it doesn't yet take in the fourth non-homogeneous boundary condition. So in order to do that, we need to do step 7, which was to plug in the non-homogeneous condition into our u of n, and we needed to solve for n and our constant, which we called a of n. So using an n equals 1 and an a of n equals 1 over the hyperbolic sine of 2 pi, we were able to then write our specific solution, u of xy, and that is just u of n with the constant a of n and n filled in. And then we were able to model what this looked like using Wolfram alpha.